guys. AP Chemistry, this is Chapter 6. This is the Energy chapter. And this is Section 1 going into the intro of energy. And we're off. Alright, energy, the ability to do work or transfer heat. Now that or could be or and. Energy used to cause an object that has mass to move is called work. And the symbol for work is a W. Energy used to cause the temperature of an object to rise is called heat. And the symbol for heat is a Q. Potential energy. Potential energy is energy an object possesses by virtue of its position in physics or the chemical composition in chemistry. For physics, the higher up an object is held, the more potential energy it has, because potential energy is dependent on height. In chemistry, the potential energy is technically in the bonds between two atoms. For example, that bond between a carbon-hydrogen would have to absorb 413 kilojoules per mole of energy in order to break, or it would release 413 kilojoules per mole in order to make that carbon-hydrogen bond. So in chemistry, the potential energy is in bonds. Kinetic energy is the energy of motion. In physics, kinetic energy is calculated as 1/2 mv squared. For chemistry, kinetic energy is technically temperature. Temperature is a measure of kinetic energy. Right? Units of energy. The System International unit of energy is the joule, not the store, the unit. A joule has a symbol of a capital J, which you came across in first year chemistry. And 1 joule is equal to 1 kilogram metered squared per second squared. There are other units for energy. You'll come across kilojoule quite frequently. Also, an older non-SI unit, still used on rare occasions, is calories with a small c. The symbol for calorie is small cal, not to be mistaken with the food calorie, which is a capital Cal. If you look on any food package, you will see capital C calorie, which happens to be equivalent to the small c science calorie of 1,000. Small c calorie is 4.184 joules. Definition of system and surroundings. The system, if you recall, will include the molecules we want to study. The system will technically be reactants and products. Surroundings is everything else. The surroundings includes any container. Or any solution if it's just a physical change where something might be dissolving in the solution. Don't forget, physical changes also have a transfer of energy. So if you dissolve sodium hydroxide in water and the water gets hot, then it's the actual sodium hydroxide pellets releasing energy to the water. Work. Again, small w. energy used to move an object over some distance is work. This is equivalent to the physics potential energy. Work, force, and distance. And of course it would require more work to push something a further distance. It would require more work if you were pushing something over gravel as opposed to a wax floor, which is related to the force. How much force does it take to push a box over a waxed floor as opposed to a gravel parking lot? And it's force acting over a distance whether you're pushing a wheelbarrow or the pistons in a car engine, which you of course are not pushing, but it's force over distance. Heat, which has a unit of a Q. Energy can also be transferred as heat. Energy is work and or heat transferred. The heat will always flow from warmer objects to cooler objects. Don't forget, this is the transfer of energy due to a temperature difference. No transfer. So heat, this is really super important, will always flow from warmer to cooler objects until they are at the same temperature. Transfer of energy. Energy can be transferred from one object to another by heat and work. The internal energy of a system is the sum of work and heat of the reaction, which results in kinetic and potential energy of all the particles in the system. You can't actually measure internal energy directly, so we measured the change in internal energy, which is going to be this symbol here, and the change in internal energy will be the heat, which is technically kinetic energy, plus work, which is technically potential energy in the macroscopic world. And you have to have your Q and your W in the right units in order to add them up. So either energy units of joules or kilojoules. Self-explanatory. I'm not going to say a lot about this. Alright, this thermodynamic quantities will have a number and a sign. The number is magnitude and the sign is direction. So you would write positive 30 kilojoules of heat or negative 10.1 kilojoules of work. Sign must always include the numerical value so we know direction. Everything will be from the point of view of the system. So in my head, I am the system and I am figuring out what is occurring from my point of view. Am I doing work on the surroundings, or is work being done on me by the surroundings? If I am the system and heat is flowing into me, then I am getting warmer, I am absorbing energy, my Q will be positive, and that's going to be an endothermic reaction. If I am the system and I am losing energy to the surroundings, then my total energy is decreasing. I am going to be a negative heat, and it is an exothermic reaction. These two you've had before. These next two you have not had before. Make sure you star them in your notes and you write them down and you block them in and get them into your head. A gaseous system. So think in your head a gas balloon. If the gaseous balloon is being inflated, it is pushing against the surroundings. Work is being done by the balloon, by the system. So that means your W is going to be negative. And we're going to do a computation for work in about 3 more slides. If the balloon is being compressed by an outside source, then work is being done on the system, on the balloon. It's being compressed. Your W will come out to be positive. If energy is flowing into the system, delta E will be positive. If energy is flowing out of the system, delta E will be negative. So of the 6, these are going to be the hard ones because these are slightly different. These apply to a gaseous system, and they all are from the point of view of the system. Definition of a state function, this one always throws me. I gotta admit I hate it. A state function, if the property of a system depends only on its present condition, it is said to be a state function. A state function does not depend on pathway. It does not depend on pathway. Doesn't depend on how you got there, only that you're there. Energy is a state function, does not depend on pathway, just the immediate condition. Work and heat are not state functions. Work and heat do depend on the pathway. Little example, climbing a mountain or potential energy. Both people climb the mountain. Both people have equal potential energy. But the guy on the right took way longer to get there. That's why potential energy is a state function. Does not depend on pathway. Alright, so a state function does not depend on pathway. A state function only depends on the condition at that point in time. So a couple of examples. We already said this. Work and heat are not state functions. Work and heat depend on how you got to that point. Energy is a state function. Temperature is a state function. Altitude, I just showed you a picture, state function. The distance walked is not. That refers to the picture I just showed you. Work done by or on a gas. Again, work, little w. If the gas is expanding, work is being done by the gas on the surroundings. The balloon idea helps me to keep this straight. If the balloon is expanding, it is expanding against the surroundings. It is doing work on the surroundings. It is pushing on against the surroundings. If the balloon is being compressed, the surroundings are compressing the balloon. The work is being done on the system, on the gas, by the surroundings. There's a calculation for work. Work will be equal to negative pressure times the change in volume. This is going to be used one of two ways. Either you are going to just flat out calculate it, or they're going to give you work and you will have to interpret it. Bottom line, the sign is super important. It distinguishes whether the system is doing work on the surroundings, expansion, or having work done on it by the surroundings, which is compression. Like super, super important. And even in class, when I'm trying to work this through in my head, you will actually see me pushing out and pushing in. Expansion, compression. Out is expansion, pushing in is compression. Now, notice pressure times volume will give you very odd units. Typically units of atmospheres for pressure and liters for volume. Well, that's a strange unit for energy, and work is energy. So you need to know the conversion factor on how to change from liter atmospheres to joules. And the conversion factor is 1 liter atmosphere is 101.3 joules. Put that in your head. Now, a couple of things I want to talk about. This is important. Expansion versus compression and of the system. With expansion of the system, and again I go with the balloon idea, even though they're not all balloons, it's just a gas sample, but this keeps it straight in my head. The balloon expands. That means the final volume will be greater than the initial volume. That means if you took the change in volume, you will get a positive number. Again, sign and magnitude. If you put a positive delta V in here, your work will mathematically be a negative value, which correlates to the system expanding or pushing against the surroundings. Now, with compression, your surroundings is compressing the system. And remember, all this is done from the viewpoint of the system. So the system, the gas sample, is being smooshed. It's being compressed by the surroundings. So its final volume will be less than the initial. The change in volume will be a small number minus a larger one. That means your change in volume will give you a negative value. Again, sign and magnitude. Now what's going to happen if you put a negative number in here and you do the math? Your work is going to come out to be a positive value, which means that the system is being compressed. The system is having work done on it by the surroundings. My advice is look this over a second time and think it through. This is probably going to be the most obnoxious concept of the chapter, but you have to know it. All right, what else? Just what I said. Write those down. Gas expands, system doing work on the surroundings. Gas compresses, system is having work done on it by the surroundings. And it really comes right down to that. This word or this word. And we are going to do a quick example. what is the change in energy, and that's internal energy, and you can't actually calculate just energy. We can only calculate change in internal energy of a system which expands from a volume of 1 liter to 4.5 liters against an external pressure of 0.980 atmospheres, while 500 joules of energy flows into the system. All right, so a couple of things I'm going to write down. Thing number 1, expansion of the system. Expansion of the system means the system is pushing against the surroundings. That means that my volume final is greater than initial. That means my delta V is going to be a positive value. That means that my work should be negative. If I do this right, my work will be negative. So I'm going to calculate work first. Work is equal to negative P delta V. It gives me 0.980 atmospheres. It gives me final volume in liters minus initial in liters. Plug it into my calculator, 3 sig figs with my answer, and I get this with some weirdo units, but that's the work. Again, the negative value. The system does work on the surroundings. The change in internal energy is heat flow plus work. Well, I just calculated work. But a couple of things I want you to know. So I'm going to box this in. This is where we're going to fill it in. Okay, if I look at the problem, it tells me 500 joules of energy flow into the system. I am not calculating the heat transfer. I am given it, so I have to interpret. Since it says flows into the system, my energy is going to be 500 joules. This is the heat energy, all right? And it is from the point of view of the system, and the problem says that 500 joules of heat energy is flowing into the system. Notice that my Q, my heat energy, is in units of joules while my work is not. That means I have to convert my work. Put this into your head. This ratio right here, this is going to be the number one mistake you are going to make. In joules, the system is doing 362 joules of work on the surroundings. Once I've interpreted these things, once I've got my correct numbers with sign, I put them into my problem. And do the math. This is the internal energy change of the system, and notice that the system gained an extra 138 joules because the sign is positive. That's it. Done for this section.